This is section 4.2, modeling with linear functions. So we're just going to dive a little deeper into applications and word problems with these linear functions. Objective 1, build linear models from verbal descriptions. And then we'll look at when we have a set of data. So we're really just going to do one example of each of these. A snack food company makes and sells donuts. The company incurs a fixed cost of $4,500 per month for rent, insurance, and other expenses. It costs 25 cents to make each donut. The company sells each donut for $1.50. Okay, so we have a fixed cost of $4,500, and then it costs 25 cents to make each donut, and then it sells each donut for $1.50. Part A, determine the cost, revenue, and profit functions. And so we're going to assume that all of these are linear. We don't have really anything to tell us otherwise. So the cost, let's call that C for cost, C of X. So X is going to be like number of donuts. I don't know why I spelled donuts that way. I'm going to spell it the short way down here. Okay, so cost is always going to be how much it costs to make one times X, so 0.25 times X, and then plus the fixed costs. So let's just talk about Y for a second. So the fixed costs are, even if you don't make any donuts at all, you don't order any like ingredients or anything like that, you still have to pay $4,500 for each month for all of this stuff, right? So then the 25 cents, that's going to kind of take into account like the ingredients that it costs for one donut, like and then maybe labor costs and that sort of a thing. And so that's going to be very much dependent on how many donuts you make. So you're multiplying that by your X. Okay, so then revenue, let's call that R. This is how much you make just selling the donuts. So you're not worried about the cost, just like before you subtract off the costs, you're going to make $1.50 times how many donuts you sell. That's your revenue. So it's always going to be your price. It's like R of X is PX. Sometimes you'll see price times X. And so then C of X, by the way, I'll just go and put in a little like model, I guess. So A is the cost per item, and B is the fixed cost. Okay, so now profit function is, profit is what you get after, how much you've made after you subtract off your costs. So for the profit function, we're going to have to take the difference. It's always the difference of the revenue minus the cost. And so this is going to be $1.50x, that's our revenue, minus our cost is 0.25x plus 4,500. And we've got to make sure that we distribute that minus sign. So this is $1.50x minus 0.25x minus 4,500. So finally, combining like terms, I'll go ahead and write P of X again for profit. It'll be $1.25x minus 4,500. Okay, so this is our profit. And then we had our cost and revenue up here. Okay, so profit, you always have to first find your cost and your revenue, and then you subtract revenue minus cost. So part B, find the break-even point. In other words, how many donuts must the company make and sell for their profit to equal 0? So the break-even point, you can think of it in two ways. To me, the easiest way is you're just going to set your profit, P of X, equal to 0. It's equivalent also to setting your revenue equal to the cost. So you break even, your revenue and cost balance out. But I think it's probably a little quicker to just use our profit function. $1.25x minus 4,500 is equal to 0. And so this is not too bad to solve, right? It's just a nice linear equation. So we can add 4,500 to both sides. So $1.25x is equal to 4,500. And then divide both sides by $1.25. So 4,500 divided by 125, 3,600. And so that was donuts, right? So we'd have to make 3,600 donuts just to break even. So if we make more than that, we will make money. We will have a positive profit. If we make less than that, we will lose money. All right, so let's look at when we have a set of data. So many of you need to take statistics, introduction to statistics for your program. Like if you're a business major, you need it. And so this is going to be kind of getting into that. We're going to look at something that sort of leads into linear regression. So finding a best fit line, but we're going to do it in a less precise way than you learn in statistics. So linear functions can be useful for modeling data that may fall on a line or at least close to a line. So if you look at this picture over here, these points are not all on a line, but they're pretty close to being linear. So we can kind of just go with it. So if we do that, then it's not too difficult to come up with a formula that allows us to make predictions. So example 2, the data below shows the number of cricket chirps in 15 seconds for several different air temperatures in degrees Fahrenheit. So basically somebody sets a timer for 15 seconds and they count how many chirps they hear. And depending on the temperature, you hear more or less chirps. And so we can look and see what this looks like. You may have heard this, how you can kind of calculate or estimate the temperature based on the number of chirps. So we have here the number of chirps, and then we have the temperature. Find a linear function that estimates the temperature based on the number of cricket chirps counted in 15 seconds. So basically, we're just going to find the equation of a line passing through, well, 2 points. We've got a whole bunch more than 2 points here, graphed over here as well. So we're just going to pick 2 points. Maybe pick the one that seemed to have nicer looking coordinates. But because we could pick, depending on who you are, you might pick the first one and the last one, or maybe, I don't know, this one and this one. That's what I'm going to pick. I don't know why, I just am. But you could get a slightly different final answer. So we should all end up with our slopes being very close to each other, and our B values being pretty close to each other, but still they could be different. Okay, so I'm going to go with 33, 66. So notice we're going to let X be the number of chirps. And then I guess I'll use capital T for temperature to be the temperature. Okay, and so then our other point that I circled up there, 2653. So to find the equation of a straight line through 2 given points, you first start by finding the slope. So we're going to do slope formula, 53 minus 66, and the difference in our x is 26 minus 33. So 53 minus 66. I should be able to do this in my head, but I don't know. I'm kind of not feeling like that's a good idea. Negative 13 over 26 minus 33 is negative 7. So 13 over 7. Okay. And that would not work out to a very nice decimal, so I'm just going to leave it like that. And then we'll just deal with figuring out our b value. And I mean, it'll be a little bit ugly, but we can handle it. Okay, so I'm going to pick then 2653 for my point. So we now know t of x equals 13 over 7x, but we want the b value, right? What's the initial value? Okay, so if we use that second point I wrote down, and I'm just picking that one because the numbers are a little smaller, then I'll set 53 equal to 13 over 7 times 26 plus b. And I'm going to be a little bit lazy with all of this. So we're going to maybe think of that as over 1. So 13 times 26 is 338. So we've got 53 equals 338 over 7 plus b. So b is whatever we're going to get when we subtract 53 minus this number. So, you know what? Well, it didn't say anything about decimals, so I guess I should stick to fractions. Ugh. Okay, so I'm just going to put this in my calculator. 53 minus 338 divided by 7. All right, it's 4.71 blah, blah, blah. But if I convert that, I'm getting 33 over 7. I guess that's not awful. I don't know why I'm being so whiny. Okay, so t of x equals 13 over 7x plus 33 over 7. All right. So then, by the way, that 33 over 7, that's about like 4.7 degrees. So at 4.7 degrees Fahrenheit, pretty cold. There's no crickets chirping. So use your function to estimate the temperature when 25 chirps are counted. So t of chirps is x, so we can just do t of 25. 13 over 7 times 25. And I'm going to make the executive decision to just estimate this to the nearest tenth. So let's do that. Nearest tenth. So 17. Oh, how did I get 17? That's supposed to be a 13. Heavens. Okay. 13 divided by 7 times 25 plus 33 divided by 7. 51.142 blah, blah, blah. So about 51.1 degrees Fahrenheit. It's a degree symbol. And part C, use your function to estimate the number of chirps that would be counted when the temperature is 77 degrees Fahrenheit. So now we're setting 77 equal to our function 13/7 x plus 33 over 7. So I'm going to start by multiplying both sides by 7. And so I get 539 equals 13x plus 33. So now subtract 33. So 506 equals 13x. And 503 divided by 13 is 38.692 chirps. Let's round to the nearest whole number, since you wouldn't really count like 0.6 of a chirp. So let's round to, I think it would be 39, yeah. So x is about 39 chirps. So it'd be a lot of chirping, because that's in 15 seconds, right? That's a lot. Okay, so there we have it.